Our first speaker is well known to the space development community. He helped Jerry O'Neill organize the first space manufacturing conference back in 1974, invented a thin metal film solar sail termed the light sail, and has lobbied in Washington for solar power satellites and against the Moon Treaty. But today he'll be telling us about a proposed manufacturing technology called nanotechnology, which promises to lower the costs of space development dramatically. May I introduce Eric Drexler.
Thank you. Well, in recent years, I have been giving many talks in which I talk about nanotechnology as a technology, focusing in increasing detail on how molecules behave, how machinery can be built of molecules, how molecular machines can be used to build other things, developing a molecular manufacturing technology base. I'm in the process of working on a book right now, and if I at any point seem a little frazzled or burned out, it's because it's a lot of work. Presently on page 252 of a highly technical thing which is going to say much more than I've ever been able to say in a talk, and which will be used for teaching a course at Cornell this fall. The mechanical engineering department, a professor there has signed on to do that, which means I really do have to get it done pretty soon. What I'm talking about today, though, is not nanotechnology, but nanotechnology for space development. In the last year, a lot's been happening. Things are beginning to move rapidly, and I think it's time to take a good, clear look at what the implications are for achieving some of our dreams. And to begin with, we need to manipulate some macroscopic pieces of technology, like a microphone. That could go off and the slide projector on. Maybe the slide projector is on, I don't know. Once upon a time, here we go. Okay. There. Once upon a time, people looked at what could be done with pieces of shaped aluminum metal and other sorts of bulk matter. And they found, first by calculation and experimentation, and then by further experimentation, that you could build liquid fuel rockets. And knowing something about engineering principles and scaling laws and the laws of physics and so on, they were able to calculate that you would be able to build increasingly large rockets and move from upgraded V2s like this, flying in the, I assume, the late 1940s or early 1950s, through larger rockets. This one looking a little bit dim because our lights are very bright here. It's actually a Japanese rocket. In the 1970s, one could begin showing slides saying, yes, we've been to the moon, what is the next step? Well, there was at that point a conceptual design. You can see this is a painting. A conceptual design which had been firmed up into rather detailed blueprints and then had nice paintings done for a reusable space shuttle. I was thumbing through a book written in the mid to late 1970s recently, and the author was confidently predicting that, yes, this would give us access to orbit at, I believe it was $160 per pound. It's been 30 times higher than that, roughly. Well, during the 1970s, we roll back to the dream here. We were going to have space transportation, and it was going to be at $160 per pound, and we could get those costs down further with shuttle-derived heavy lift launch vehicles like these. And with those, we would, of course, move on to build a station in Earth orbit, and from that base, go on to the moon. The moon, of course, is full of resources, and one can plot out schemes involving transportation from Earth and to the moon and from the moon, with mass drivers on the surface of the moon to mine lunar materials and set up large-scale space manufacturing. I participated in a number of studies of that in the 1970s, and I guess I'm still studying manufacturing, but in a slightly different direction. So one could plot these things out and describe how one could accelerate mass off the moon with electromagnetic devices. I'll be talking more about some of these concepts tomorrow. I've been invited to give a bit of a retrospective on the ambitious space settlement concepts as they initially emerged in the 70s. And here we have a mass driver on the surface of the moon. And here we got as far as cutting metal and making a model mass driver at MIT with Jerry O'Neill and Henry Colm in technical direction, and in the middle there, looking a little hairy as me in an earlier incarnation. Well, if you have materials in space and can build in space, you can lay out agricultural areas and grow plants, and for those who aren't vegetarians, raise animals, and or at least have milk, I suppose, and have self-sustaining settlements in space, like this kilometer-scale torus designed at the 1975 summer study, which would house 10,000 people and be large enough to have open space inside. And there were plans for various rotating structures weighing in the many thousands to millions of tons. And you can see a wine and cheese party in the foreground there, as was done by an artist at NASA Ames. And large cylindrical space settlements through which one, kilometers in radius, with sunlight being blown in, spinning for artificial gravity, air, and inside, land. And this also obviously was done by a California artist. Well, all of these things are physically possible. The strength of materials and the laws of physics say that you could do this sort of thing with 1970s technology, if you could build enough systems on a large enough scale at a low enough cost. Well, all of this needed some economic justification, clearly, and it was so plans for space industry were examined in considerable detail. A lot of work was done on designs for solar power satellites, large structures built in space, again kilometers in scale. That sort of round antenna there is 1 kilometer in diameter, which would beam billions of watts of power back to Earth. And these, of course, were the days of the energy crisis. And also, some character proposed building thin metal film solar sails and tooling around the inner solar system without expending any fuel. They seem to have potentially low costs. If you could manufacture large structures in space, kilometers wide, but with a mass of only about a ton, these could be used to fly to the asteroids, this actually being a moon of Mars standing in for an asteroid. Since we haven't yet flown a mission to an asteroid, though we will soon, in progress. And their facilities can be built in space to refine out valuable metals. Things as low value as nickel, iron, steel, and as high value as platinum group metals. And of course, there are also dreams of going on, or back from the asteroids, I guess, to Mars. And you can again see solar sails in the sky, since this is a JPL proposal. Well, the first step, of course, was to build that space station. Yes, we'd use the space shuttle and go up and put together a set of pressurized living spaces and solar panels, and be able to do experiments and refueling and construction in space. And to do this, we would build a space station which would have some panels and pressurized volumes, and you'd be able to, well, first you'd build a space station which might look like this with some pressurized volumes and, well, but then again, also, maybe, yeah, okay. All of those designs are no later than the early 80s. None of those represent the current series of revisions that Space Station Freedom has gone through. This design is again a set of pressurized canisters and solar panels. It looks larger and more ambitious than anything on the drawing boards in this decade. And if you look closely, you'll see that that shuttle isn't the shuttle they actually built. That is a conceptual design that preceded the firming up of the design for the present space shuttle. Well, it seems we've been at this for a long time, and that by a lot of measures we're not making much progress, and I would like to discuss why that is in terms of our technology base. Well, we're using aerospace technology with conventional manufacturing techniques being pushed to their limits in many ways in terms of precision, reliability of manufacture, lightweight. And we end up with systems that are made out of metals because metals are tough enough that they can work even though they have some flaws in them. They're not brittle as the really strong materials are. They're handcrafted, and they're just barely able to reach orbit while having both a safety margin and a payload. And if you want a bit more payload, you end up with a bit less safety margin. And we know that these things operate rather close to the margin. This is an early rocket explosion, and when I gave a version of this talk rather recently, and finally saw the enlarged view of this slide, which I hadn't shown for some time, I found that it was in fact the Challenger. Well, this was here to illustrate the problems of maintenance and turnaround. We build these systems and we put a tremendous amount of effort into each flight. If you look at the present day airline transportation industry and the aerospace industry that backs it up, you find that a very small fraction of the American population works on building and maintaining and flying aircraft. And yet we fly enough aircraft that, roughly speaking, everyone in the country can fly something like once a year on the average. If everyone in the country, not a small fraction, but everyone in the United States were working full-time on the shuttle program with its present productivity and costs, and everyone took turns to fly on the system that they were all working on, you would get to fly about once every 5,000 years. Space Station Freedom, if you take the sort of the average of the most recent NASA estimate of cost and GAO estimate of cost, and ask, how many salary years do you have to save up your nickels and dimes, that is, all of your income, to spend one lifetime aboard that space station? The answer is on the order of 1 million salary years. To achieve the goal of a spacefaring civilization that allows us to live and work in space, large-scale space settlement, we need something like a 5 order of magnitude improvement in cost. That takes a while even in the semiconductor industry, unless you get a new technology base, something where such that you can't just talk about extrapolations of the cost. We got a 6 order of magnitude increase in the power per pound, the energy per kilogram of an explosive in 1945. And it wasn't done by incremental improvement of the previous chemical explosive technology base. It was a new principle. It seems that we are presently in sight of a new principle on which to base manufacturing and on which to base, more broadly speaking, a technological civilization. I would like to briefly outline that. Again, this is a talk on nanotechnology for space rather than a talk on nanotechnology, and so I will be brief. This is our present technology base, by the way, just for comparison. It has some characteristics which can be pointed out here. First of all, the parts tend to be large enough that people can manipulate them with their hands. And the second is that the manufacturing system is full of animals. You can see that there are 4-legged animals in there, and at a higher grade of capability in various ways, there are 2-legged beasts, which are still mammals. And they're in there in the middle of the manufacturing process. That means that things are slow because hands only move at rather limited speeds. It means that the fineness of structures that can be worked with is very coarse. Well, we need a new manufacturing technology base. Now, yes. Back in 1959, Richard Feynman said that the principles of physics, as far as I can see, and he got a Nobel Prize subsequently, so I guess they decided he could see pretty far. The principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. And he pointed pretty much in the direction of the modern concept of nanotechnology, though it was sketched in just a couple of paragraphs at the end of a talk that he gave at an American Physical Society meeting in, again, December of 1959. Well, is it in fact possible to maneuver things atom by atom? Well, IBM seems to think so. This is the surface of a nickel crystal. In the upper frame you see a bunch of xenon atoms scattered around it, and in the successive frames you see emerging the letters IBM. This was done with the scanning tunneling microscope, which is one instance of the broader class of scanning probe microscopes, or proximal probe microscopes, including the atomic force microscope. And a characteristic of this fabrication process here is that it is precise in a molecular sense. Everything is precisely arranged. A word for that is eutaxic, Greek for well-arranged. Each of those atoms is sitting in a unique dimple in a locally perfect nickel crystal. It's either in one place or it's in another. It's in the right place or it's in the wrong place. And they fiddled with it until all of the atoms were in the right place, and then proceeded to publish the results in Nature. Well, this direction of research has been drawing increasing attention over the years. I've been working on this since 1977. A couple of years ago, Japan's Ministry of International Trade and Industry said that control technologies for the precision arrangement of molecules are a basic industrial technology for the 21st century. I might add a couple of brief quotes from the journal Nature. February 7th, headline, Nanotechnology. MITI aims at small research. Dateline Kyoto. Last week saw an unusual little gathering of biologists, physicists, and chemists in Kyoto to discuss atomic-level design of functional structures. And it goes on to say that this is just one example of blossoming interest in Japan in nanotechnology, a field which, with the backing of the powerful Ministry of International Trade and Industry, seems destined to become Japan's next priority target for industrial research. The most recent copy of Nature to turn up has a number of items here. It says that AIST, that's I believe the Agency for Industrial Science and Technology, AIST's decision to establish an atom factory, quote unquote, in a new research center in Tsukuba is part of a massive move by MITI to promote research into nanotechnology. MITI officials are now sketching out a large-scale project that, with the collaboration of dozens of companies, will plow hundreds of millions of dollars into the development of, here they call it, angstrom technology. And they're also setting up a research center in Tsukuba, which, yes, that was mentioned there. So, where a year ago, these were some concepts that had been talked over for a number of years. This year, there are a set of concepts that are on the edge of having hundreds of millions of dollars poured into them, into the early stages leading in this direction. Now, the early stages grow out of existing chemistry and biochemistry and micro-positioning, the scanning probe microscopes. There are various paths that lead forward from that through to devices that are able to finally let chemists or engineers or whatever you want to call the people who are doing it, finally let designers take molecules and put them where they want them. Not put them in a solution, shake them around, and try to do clever things to make them assemble together in the right patterns, but instead, as in conventional manufacturing, take the pieces and put them where you want them, one after another until you build something complicated. We've never had that capability before. It is clearly within reach today. A schematic design for a device able to do that would start with an atomic force microscope, which can already move a tip around to atomic precision near a surface in a liquid, and mount on the tip of that device a molecule which can serve in effect as a gripper for reactive molecules, so as to put them in specific places to build things. That illustration is a scheme which I published a short piece on in Nature in collaboration with John Foster of IBM's Almaden Research Center. This month's Journal of Vacuum Science and Technology B has a vastly improved version of a device able to do this kind of activity, which is something that I designed last summer and has now found its way into the journals. Well, that's a first step. What kinds of things can be built? And this is just a general sketch of technology background. We know from looking at nature and in the laboratory that molecules can form machines. We see molecular bearings, things that let one part rotate with respect to another. Rotary motors, which is how bacteria swim. Some bacteria can swim. The way they swim is that they turn a propeller with a motor. Helical rod of protein which serves as a propeller. There are linear motors, which make one fiber slide past another. That's how your muscles work. Things in that class can also serve as conveyor systems, and we see in the cell programmable machine tools, devices that contain on the order of 100,000 molecular fragments put together to form a thing called a ribosome, which is programmed by DNA indirectly through RNA to build other components which can serve as components of machine tools. The device that I showed a moment ago in its current version could build something as complex as a ribosome, but more flexible. A first generation of machine tool of the sort that lends itself to design, to human use for design and construction of complex molecular machines. Well, further down the technology path, and now we're not at one jump up from the bottom box, but up in the top box on that diagram I showed earlier, would be rigid robot-style positioning systems. This is a sketch of a design and the peculiarities of the design relative to industrial robots fall out of its requirement for extreme rigidity to avoid positional fluctuations due to thermal excitation. This is a 6 degree of freedom robot arm which can be built on a scale of about 100 nanometers and can position reactive fragments to build complex structures. The range of motion on such a device would be something like this. You can go through and look at the compliance, the reciprocal of the stiffness, the sort of the budget for the flexibility of the arm, and show that it turns out to be, in fact, stiff enough to do its job under the conditions that it has to at room temperature. What can be built with devices like that includes computers. Again, we're in the top box of that chart, building very complex structures with molecular manufacturing. You see there the scale of a typical human cell, about 20 microns. In the lower right-hand corner is a 1 cubic micron volume labeled mainframe computer because it has enough room to hold actually I guess it'd be depending on whether or not you want to include a disk drive equivalent, it's either the equivalent of a 1980s mainframe with storage, or the equivalent of a 1990s mainframe without the mass storage system. And in analyzing things like that, one ends up working with expressions like this, which the upper one describes the positional uncertainty of an extended rod under the combined effects of quantum mechanics and thermal noise. And it turns out that the lower expression is an excellent engineering approximation. Thank God. And this stuff has found its way into the hands of people with airbrushes, such as the artists who work for Scientific American, who some time ago did this picture of two small submarines cruising down a capillary with some bright red blood cells there, and each of those submarines has enough room in its belly for a mainframe computer and a database that contains more information than the human genome, a gigabyte class database. Well, to see that there are reasons for pursuing this technology base short of being able to build large aerospace systems, I'd like to say a few more words about what can be done with computers. I showed some very small computers. The question is, what can you do with nanocomputers on a more macroscopic scale? It turns out that in a cubic centimeter, you have room for about 1 trillion CPUs. That's some hundreds of mainframe class computers for every person on the planet today, except it's all in 1 cubic centimeter. And if you go through the calculations of energy dissipation and so on, you conclude that yes, you can supply it with power, yes, you can cool it, and that the total computational power that can be put in scaling from this, you'd want to go to a lower power consumption, fewer CPUs, etc. You could put more computational power than exists in the entire world today, including all of the supercomputers put together, into a laptop. That presumably will speed up computer-aided design at least somewhat by making the models run faster and allowing it to model more complex systems. Well, that already is somewhat macroscopic. Again, that's after moving through from the generation that we're at today, chemistry, biochemistry, micropositioning, up through what I showed earlier as a hybrid protoassembler. That's a generation of technology which, well, I talked to experimentalists in the relevant disciplines, the people who are doing work with the atomic force microscopes, with binding proteins, with immobilizing molecules and attaching them firmly to a mechanical substrate, or at least to a best place to do that latter task, which turns out to be apparently the hardest. And I say, well, it looks to me as though you should be able to build this. And they say yes. And I say, well, it looks to me as though it might take several years with a number of people involved that would require funding at the level of maybe $1 to $2 million. So, say 4 years plus or minus a couple at $1 or $2 million per year buys you a hybrid protoassembler. At that point, you're on the first solid rung of the ladder to advanced molecular manufacturing, though there are a lot of intermediate steps to go through. Well, after you've gone through those steps, you have devices like the robot arm that I described earlier. The question is, what can those do for you in terms in comparison to present-day manufacturing? And there you can make the comparison to present-day robotic devices. And you find that in mechanical systems, if you reduce the length scale of them by a certain factor, like 10 to the 6th, that the frequency of operation increases by a factor of 10 to the 6th. This holds true for tuning forks and disks that are spun up to a speed that's some fraction of their braking strength, and many other elementary physical systems. It also applies to more complex systems. The components that can be manipulated by a device which is that small and which is working with molecular tools are molecules. which are fundamental building blocks of all matter. They're not things like nuts and bolts, which have properties which are limited by some earlier stage of atomic assembly that you didn't control, heating things and beating on them with hammers and the like. So you're working with fundamental building blocks, which means that you can build almost anything if you have control of where you're putting those building blocks. They're inexpensive. Industrial chemicals, which consist of small molecules, cost in the dollars per kilogram range or often less. And obviously they're abundant, found in vast quantities. So you would have an industrial base which, instead of requiring as its inputs relatively complicated fabricated pieces, which in turn had to be made by earlier pieces of the industrial base, and which, instead of operating at something like 1 step per second, instead has prefabricated components that are abundant. It operates at 1,000,000 steps per second. If a device has 1,000,000 pieces in it, and it operates at 1 step per second, or a factory has 1,000,000 pieces, and it operates at the components of it work at 1 step per second, it'll take it 1,000,000 seconds roughly to build a copy of itself, or to build as much product as it itself contains, even if it's building something that's different from what it is, but kind of similar. If all the components are working at 1,000,000 times the frequency, the time required for a system to produce its own mass in comparable product isn't 1,000,000 seconds, it's 1 second. So what this says is that this is a manufacturing technology base, which is, in a very basic sense, 1,000,000 times more productive than the manufacturing technology base we work with today. And it's one which can produce a range of materials and products which we're simply unable to make today because we lack the ability to arrange atoms in those patterns. So today, our fabrication abilities are very strongly limited by our technology. In the future, it seems that one will be able to fabricate most stable structures, and I just finished a 69-page chapter which lays that out in detail for organic chemists. And will be critiqued by organic chemists rather thoroughly in the next couple of months. And the chief remaining design limits at that point seem to be physical law and what we're able to actually manage to design. And so the claim is that a reasonable working definition for what nanotechnology means in practice is that it will mean, nanotechnology, or alternatively molecular manufacturing, will mean thorough and inexpensive control of the structure of matter. Inexpensive because the raw materials are inexpensive, the capital plant is highly productive, and the capital plant can, among other things, produce more capital plant. You run through the cost loop and you find that it doesn't depend on present aerospace systems. If you want to make an estimate of their cost, you find that you have to look at our existing technology base of manufacturing. You have to look at the very difficult to estimate costs of handcrafting or automating the process of manufacturing many different components, inspecting them, doing piles of paperwork. And so it's not really credible to believe that you're going to see a dramatic cost breakthrough because you're tied to this known expensive technology base. This technology, however, does not draw on fabricated products from our existing technology base. It is, in a technological sense and in an economic sense, relatively autonomous. It's possible to make cost estimates that are internal to this technology base. If you design a new rocket, you can't say, well, because of this new rocket design, the rocket is going to be cheap, because the rocket design is made by the same old manufacturing plant. With this technology base, you can say, because of the nature of this technology base, it's going to be cheap because it makes its own hardware, including the manufacturing hardware. And that's a fundamental difference, and I need to learn how to say that in fewer words. But I hope that distinction has somehow been spit out of my mouth here. Well, among the things that you can make with this technology base are structures that contain fibers and components made of diamond. Flawless diamond. So, one of the things you can make is a fracture-tough diamond fiber composite with most of the volume fraction being diamond. That turns out to be a remarkably big win for aerospace vehicles and many other things. Just to talk about a few things before I get to the aerospace vehicles per se, this is a piece of airbrush work done by Time Life Books in consultation with me a while ago. This is a picture of a spacesuit with a blow-up of the fibers that make up the spacesuit. There's obviously a continuous sealing layer in there someplace, but most of the mass of the spacesuit is this three-dimensional weave of structural fibers. But the fibers are made of diamond. But it's not just any diamond, they're little mechanical diamond components, which are hooked together like screw jacks with little motors and controllers so that they can extend and contract. As a consequence, you can have materials that can change their shape. They can have the strength even after you have all of the weakening associated with the joints and the fibers and the motors and so on, which still have a strength which is greater than that of steel, an overall strength, but which can have that strength and simultaneously change shape. That's good enough to let you build a spacesuit which constantly stays just barely out of your way as you move. So it's as if you're not wearing anything at all. And it holds atmosphere. And it's not at all like one of these inflated, bulky, stiff things. Instead, it would make working in space as comfortable as working outdoors on a nice spring day. Well, on a large scale, you have a tremendously productive manufacturing technology base, which can manufacture more manufacturing technology base. You can build large things. And Timeline Books did this illustration here of an asteroid with some little conveyor systems wrapped around it, pulling off materials, and a large solar panel, and these materials and energy being supplied to a construction system which is making a multi-kilometer scale space settlement. It seems that such things, once one has the technology base and the software to control it, will be inexpensive. And here is their artist's concept of lots of little machines working together to build a honeycomb structure which is part of a rocket engine. A couple of words on space systems. Here's the shuttle as a marker for that. I have a sheet here which some of you should grab from me on engineering parameters of relevance to aerospace systems, which come out of this body of work, focusing primarily on materials properties. And I got stuck in Dallas-Fort Worth with thunderstorms for several hours on the ground coming here. And during that time, I had my calculator, and so I worked through the exercise, which I have at the end of that sheet. The exercise says, design a single-stage orbit vehicle with a dry mass of about 1,000 kilograms. Well, I sat down and started going through the design loop and looking at specific impulses and structural mass fractions, and I said, well, okay, let's say that we have a payload of 400 kilograms. Which with very lightweight structures and other things is sufficient to have a four-passenger vehicle. Okay? Payload, cabin mass, 400 kilograms. When I was done with that design exercise, I found that I was having trouble, given the assumption of materials with a strength-to-weight ratio 80 times those of a really strong grade of aerospace aluminum at room temperature. I had trouble getting the vehicle dry mass above 50 kilograms. The vehicle gross liftoff weight, it's a winged vehicle because wings are very lightweight and cheap, so it can go through by ordinary air-breathing engine subsonic cruise mode up to a nice high altitude to get above most of the atmosphere, which is the main problem with a small vehicle, is pushing through the air. The gross liftoff weight, it seemed, wanted to be about 2.5 tons. This is for 4 people to orbit, single-stage orbit, fully reusable vehicle. The same technology base, running some rougher numbers, suggested that you could, well, the Saturn V system got 3 people to the moon and back with an enormous vehicle. This technology base could have a fully reusable vehicle, direct descent to the moon and return, 15 tons. And to see why that is, by the way, for those of you who are noting that stiffness is often what's important rather than strength, and I said a factor of 80 in strength, it turns out it's only a factor of 15 in stiffness, but you can have active structures made with this technology base that simulate, give or take, material strength limits and frequency limits that simulate essentially infinite stiffness within your measurement accuracy. So you can get a factor of 80 both in stiffness and in strength. Imagine taking the space shuttle and taking its structure, all of the structure and its engines and everything else, and cutting that mass by a factor of 80. If you did that, your payload would go way up. But if you wanted to keep the payload fixed, you could now shrink the amount of fuel on board by a large factor. But once you've done that, you now need less structure. And if you go around that cycle a few times, you conclude that you can put the same mass in orbit with a much smaller vehicle. Then you ask, why do you want to put so much mass in orbit? If your vehicle now has a mass that's 80 times less, then quite plausibly your payloads do too. And I think that sketch of a cycle of change starting with the shuttle design should make the numbers I quoted a moment ago plausible. The other number that should perhaps make those plausible is that the mass of fuel comes right out of the familiar rocket equation. And the structural mass, well, if the structure weighed 80 times 50 kilograms, the structure would weigh more than the fuel. In an aerospace practice, the structure weighs much less than the fuel, so obviously the structural mass fraction, given the factor of 80, is very conservative. So, if products are dollars per kilogram, and a 4-person single-stage orbit vehicle is 50 kilograms, and as it turns out to be the case, the amount of energy needed to make that amount of LOX hydrogen is an amount of energy that you can get with 6 or a dozen square meters of solar cells for 1 year. It would seem that travel to space does not look so difficult anymore, if you have the technology base. Well, we've seen the first steps toward that demonstrate that this kind of technology base is coming into reach in molecular engineering, in the biological world, which I haven't emphasized here, and in the more vivid scanning probe microscope world. There are a series of steps which are now laid out to the point where you can understand them fairly well, or we can understand them fairly well. It seems that in a modest number of years we can be building complex molecular devices with a turnaround time in the construction that is comparable to the turnaround time for revising a piece of software, compiling a module, linking, recompiling, linking, and doing some tests. We're talking about hours to days to do an experiment. The cost of the equipment is already easy to estimate for that first generation because most of the cost is an atomic force microscope. Those are on the market today. They're about $100,000. The cost will be falling in the coming years as more companies enter and competition begins. So the costs are in the same range as the costs for a high-end workstation after you allow for a little bit of cost reduction. So costs for equipment similar to those of computers. Times required for an experiment similar to those required in software development. Materials costs for an experiment are about the same as those required for software development, meaning the amount of material is in the micrograms. The complexity of the things you're building, well, 10 to the 5th little building blocks put together is a reasonable number. A complex program has 10 to the 5th lines of code. But one of these little building blocks is just an inert thing that's part of a much larger structure. Whereas a line of code is an active thing, which each one of which is a major act of creation, or at least a minor act of creation to put it together, and it's very difficult to figure out how the whole system behaves. Each line of code is roughly equivalent to a moving part. We're talking about the second generation systems would have maybe 6 moving parts rather than 100,000. The long-term systems would be as complex as a modern automated factory with many parts, but again, clearly within the range of our ability to design. And so if, within a few years, we're beginning to do experiments where the costs and times are comparable to those in software and the complexity is less, I think that 5 years downstream from that, we're going to see some rather dramatic developments, including new generations of tools which are even faster. And by then, sophisticated computer-aided design tools that help people know what it is they'd like to try doing with these tools. And with turnaround time so fast that you can try something and the next day find out that you did it wrong and try again, instead of, as in aerospace, waiting 7 years to find that you built the wrong system. I think progress can be very fast indeed, and after yet another 5 years, which now puts us about 15 years into the future, it is quite plausible that we'll be building things that are capable of building large-scale structures of diamond fiber composite at dollars per kilogram. Well, this can make a large difference. We've been talking here about molecular machinery. You can see a lot of green in that picture. That green is solar-powered molecular machinery, which is in large measure responsible for such a massive feature of our planet as the composition of the atmosphere. I might mention in passing that this technology can be as clean as plants. Many environmental issues look much more attractive with this technology base than they do with our present industrial technology base. I should also point out the obvious, which is that any technology this powerful lends itself can be abused, and that the abuse of an extremely powerful technology can do great harm, and that one of the reasons for paying serious attention to these matters before they actually arise is that there are some dangers out there that we desperately need to avoid. And I'm not emphasizing those here today. I'm emphasizing what we can do on the positive side, but the potential for abuse is another issue to keep firmly in mind. And so it seems that it will in fact be possible to make the Earth a better place and to leave it, and to build the large habitats in space that have been dreamed of by a number of people in this audience, I believe, since the 1970s. I'd like to close with a little bit of historical perspective. Once upon a time, if you wanted to have the sound of a flute in a room, you needed to have a flute and a flute player. And if you wanted to add the sound of a violin, you needed a violin and a violin player. And if you wanted the sound of an orchestra, the sound of a symphony, you needed many instruments and many people. It was very expensive, and it was a very, very special occasion, especially if it was in your home. Well, today, in our homes, it's very easy and inexpensive to have a device which, driven nowadays by digital data, acts as a universal sound-producing machine, and it can produce any sound that you want. Well, once upon a time, if you wanted to have the shape of a letter A on a piece of paper, you needed a piece of metal in the shape of a letter A, and if you wanted the letter B in a particular typeface, you needed the shape of the letter B in a particular typeface, and these things would be put in little trays by skilled people working one bit at a time. And this was a big improvement over writing by hand, but still it was relatively slow and expensive. Today, again at a price range that can be afforded in the home, you can have a device which, driven by digital data, can make any pattern of black marks on paper you want, any typeface you want, and diagrams besides, the laser writer. So we now have general purpose page-making devices. Well, today, if you want to have a piece of metal in a sort of a cylindrical shape and with some change in diameter and so on, you need to have a lathe and a lathe operator. At least a few years ago, you needed the lathe operator. Now you need somebody to maintain it and program it. And likewise, for a more complex piece of metal, once upon a time, you needed a milling machine operator. And if you wanted a piece of sheet metal stamped in a particular shape, you needed a die. And if you wanted the symphony of an automobile or a space shuttle, well, you had to have many, many instruments and many, many skilled performers to play those instruments for you over a period, in the case of the shuttle, of years. But one of these days, we're going to have, I believe in the early 21st century, general purpose thing-making devices. And that will make all the difference, because while a CD player is not a sound, and a laser printer is not a printed page, a thing maker is a thing. Thank you.
Since the speaker has been astoundingly efficient in his information transfer rate, we have 15 minutes for questions and answers. I understand you would like to recognize your own questioners.
That would be fine, except that actually questioners over there are going to be at a great handicap because I can't see them unless I hold my hand here. So perhaps someone else should do the question recognition.
I can't see over there.
Okay. Would someone like to stand over there and direct out? Thank you. Okay, questions? Yes? Please.
Current language of manufacturing
The question regards the extreme cleanliness required in modern microfabrication, which is working on the scale of microns and increasingly down a bit into the range of hundreds of nanometers. The observation is, and I will state it more forcibly, that to do the kind of manufacturing that I've described will require even greater cleanliness than that, even greater control of the environment. How does one do that? Well, in the short term, the first steps on the ladder that I described, it turns out that operating in solution with relatively pure materials and building relatively small devices, that present-day precision or highly refined chemicals seem to be adequate. That kind of solution environment is all right. One of the reasons for that is that you're not trying to control a whole square centimeter with great reliability. You're trying to control a much smaller area. So you can have a much higher density of contaminants per square centimeter and still have very low probability of having one where you're working. So in that sense, it's more relaxed. Another advantage is that working in solution, which is the first generation, things don't stick together as well when there's a solution around, basically because all matter attracts, and if there's already liquid there, everything is already happy because it's surrounded by matter. Van der Waals attraction and Haymaker constants and various things describe that. Longer term, the concept is to have devices that work very rapidly in a perfect local vacuum. That perfect local vacuum, however, doesn't have to be a very good vacuum on a macroscopic scale. You just have to have no stray atoms in a very small volume. That doesn't require too low a concentration per cubic meter. And indeed, one can describe very small vacuum pumps, walls, and show how those conditions can be maintained. Yes.
You were predicting orders of magnitude increase in speed of manufacture, I believe, and I didn't quite understand how that came about. Can you clarify that a bit, please?
Okay. The measure of productivity. The question is, how does one get orders of magnitude improvement in speed? First of all, the measure of speed that I'm using is how long does it take a system to build another system or a quantity of product which contains a comparable mass and complexity to the manufacturing system. How long for a manufacturing plant to produce a pile of hardware that is in kind of tonnage and complexity roughly comparable to that of the manufacturing plant itself? The argument is that depends on how long it takes a machine to perform an operation. If it takes 10 to the 6th operations for a machine to build something as complex as itself, then if those operations are faster, you get done faster, and it's more productive by this measure. And the characteristic frequencies of these very small systems are roughly 1,000,000 times higher than the characteristic frequencies of macroscopic systems, and the productivity falls directly out of that. I should mention, before I forget, that people who are interested in more information in this subject should certainly drop by the Foresight Institute and Institute for Molecular Manufacturing table, which is opposite the elevators on this floor. There are a lot of publications there, and people are invited to join and contribute in that manner. And also, we're getting ready to start up a National Space Society special interest group on the national level. There will be a workshop tomorrow at 2 o'clock, and you're all invited to that. But on with questions. Yes?
How is power transferred to these devices? Is it a device? How do you power them?
Getting power to these devices is clearly one of the essentials. The two most convenient ways of doing that are, for a fixed device, you can have it connected by electrical conductors to a source of DC power. DC power at 5 volts suffices to drive electrostatic motors with a power density of 10 to the 15th watts per cubic meter. So you can in fact take DC power and convert it to mechanical power very efficiently. The other approach is conversion of chemical energy. One can have mechanical systems that take molecules and smoothly transform them into other molecules. If in the process there is a release of chemical energy, that energy appears as shaft power. Yes?
In microchips, you have a problem with electrostatic discharge that destroys your small molecular or near molecular level machinery. How would your nanotechnological tools deal with stray static? On that scale, a 300-volt static charge walking across a carpet would be lightning bolts.
Yeah. Just to emphasize the magnitude of of the potential problem because of the difference in scale. The difference between nanometer scale and micron scale, the difference between nanotechnology and microtechnology, is roughly a factor of 1,000 in linear dimension, which is a factor of 1,000,000 in area, which is a factor of 1,000,000,000 in volume per device. So if microtechnology makes elephants, nanotechnology makes ladybugs. With respect to static charge destroying things, that is a problem in chips because chips are electrical devices with conductors running out over macroscopic distances. You can touch a conductor here, the voltage goes, from the static discharge goes straight into the chip and fries a small device. If you were to instead have your chips electrically isolated in an electrically isolated box, Faraday cage, and communicate with them optically, for example, you would have no static discharge problem because things that you did outside would not affect what was inside. That kind of strategy can be used for small-scale devices. If people were really concerned about electrostatic discharge problems and really wanted to make consumer hardware robust against it, they could, but it would cost something. In this case, manufacturing is so cheap that you can just go ahead and build it right. Yes?
Eric, perhaps we could summarize some of the efforts and frustrations involved in getting more funding for research on the subject here in the United States, particularly government-by major corporations other than IBM, sort of the community last year.
I'm asked to summarize the situation with respect to funding in this area of the United States, and I think you said frustrations in this area. Thus far, a lot of the work has been theoretical, and it has not been funded by appeals to miscellaneous grants agencies. This year, though, seems to be, I think, in light of Japanese efforts, in light of advances in the technology base, in light of improvements in the understanding of what can be done, this year, I believe, is the year to start pursuing serious R&D funding for laboratory work and detailed computer modeling. The Computational Nanotechnology project, which just got started at Xerox's Palo Alto Research Center, is doing some computational modeling in collaboration with people at Caltech. Those sorts of things are ripe for funding. A modest number of millions of dollars could be absorbed by all sorts of other people, I'm not saying me, I'm saying them, to do useful things that would advance us on this technology path. I think that in the coming months, we're going to start seeing some of these groups with aid from the Institute for Molecular Manufacturing, the Foresight Institute, and the new NSS Special Interest Group, beginning to put out some feelers to funding agencies and making the case to them that this seems to be arguably the manufacturing technology of the 21st century. The technology that will finally get us into space in a big way. The technology that will replace the integrated circuit. Shouldn't the United States be spending something on this? And I think people will fairly soon start saying, yes. But they need to be pushed. And I think that people in this room can help doing that, can help that pushing.
You alluded to some dangers that we need to be aware of. What do you yourself believe to be the major dangers?
Well, the question regards the dangers of this technology and what is of greatest concern. An idea which has been floated, actually it was originally floated by me, which I think is overemphasized, is that one might make little uncontrollable things that would be self-replicating and be like little germs. That's a physically possible thing to do. If someone does that, it's a very, very bad idea. But the motives for doing anything like that, the economic motives, the scientific motives, the technological motives for building anything even slightly resembling such a device are so slim that a little bit of regulatory pressure should keep anyone with goodwill and a grain of sense so far from building anything like that. You can do molecular manufacturing, build spacecraft, have things that do anything you could imagine those devices doing. You can build things that serve all of those functions without building a device, anything like that. So the real danger, I think, is people who are deliberately and grossly irresponsible, or more likely are developing systems that can be used for destruction for the classical purposes of achieving power over other people. Basically, military systems in the hands of aggressors. That kind of abuse, I think, is the central concern. And that kind of abuse is a reason for trying, in any way that we can, to ensure that these developments are done in an international cooperative fashion to minimize the chance of sliding into an unstable arms race. not because cooperation is necessarily just a wonderful thing for its own sake, but because one of the things that an intimate cooperation does is it provides you with a natural, comfortable, and productive form of mutual on-site inspection. If we are going to have that situation, I believe that the United States needs to have a strong presence in this field of research so that we will have something to bring to the table in cooperation and cooperative efforts. Yes?
What are some specific examples that have already been developed? And what does this envision?
National Institute of Standards and Technology? Yeah. The things that have been developed thus far are, well, proof of principle of innumerable unit operations at the molecular scale. Synthetic organic chemistry is full of steps which can be adapted to construction in this fashion. We've seen the engineering of structures that contain thousands of atoms in the protein engineering world and making those, again, as precise eutaxic structures. We've seen in the scanning probe microscope world atom-by-atom manipulation. So all of those are the base of what's been demonstrated. The National Institute of Standards and Technology, NIST, includes a gentleman by the name of Clayton Teague, who is the editor of a journal called Nanotechnology. By the way, the term nanotechnology is often used for extreme microtechnology, which is qualitatively very different from molecular nanotechnology. So beware of that confusion. When someone says nanotechnology, they don't necessarily mean anything that contributes to this. Though sometimes they do, they actually mean both in the same breath. In any event, Clayton Teague clearly means by nanotechnology both the extreme microtechnology and advanced molecular nanotechnology. He's the editor of that journal. They're going to be publishing the proceedings of our next conference. We're having a conference at Stanford, co-sponsored by the University of Tokyo Research Center for Advanced Science and Technology. And inside NIST, they're certainly doing work in this direction. Also at Naval Research Laboratories, there's some interesting efforts at molecular scale control of the structure of matter.
Last question, Eric.
Yes? Dates of the conference. Some point in November, I don't have them memorized. That information is among the information available at the, yes? 7th through 9th, I'm told, by the Executive Director of the Institute for Molecular Manufacturing, which has $175,000 of seed money, and if it is going to serve its function of promoting research in this area, needs additional help. Thank you.